Hey guys, welcome back. Hope y'all enjoyed your first day of class and are hanging in there so far. Just want to go over a little bit more in depth some of the things you may have talked about. By now, you've probably talked about the discovery of isomers kind of in the history of OChem. And isomers are compounds that have the same number of the same kinds of atoms, but they have different physical properties, so they behave differently. And that leads us to conclude that, oh, well, it must matter how these different atoms are joined together. Therefore, bonds. So, why do atoms even make bonds? A lot of it really goes back to the root of what we talked about last time, the particle nature of the nucleus versus the cloud-like nature of the electron. Because like we talked about with electrostatics, in order for something to be completely electrostatically satisfied, that positive and negative charge really wants to be as close together as possible. And in our situation with the atom, if that were allowed to happen, then what would happen was the particle-like nucleus with our positively charged protons, it would be as if we had stuck them right in the very middle of this balloon before we had blown it up. And then we were able to compress the balloon right on top. But we know we can't do that because the nucleus has a particle nature, while the electron, on the other hand, is like a cloud. So we can't make it collapse down on top of the nucleus. So that's where bonding comes in. And a good way to think about bonding is kind of like kids and candy. Most kids like candy. And so, let's think about it as if the kid were our particle nucleus and the candy is going to be our electron. So just a kind of way to simplify it down so we can understand things a little better. So in the ideal situation, just like we talked about, those positive and negative charges would be right on top of each other. That positively charged kid would get to hold that negatively charged electron. So this is the ideal case. But, however, because of the difference in the nature, they're not going to be completely satisfied because the kid can't get a hold of the candy. So, here's our real situation. So, in order to make this better, two nuclei, so here we have two children, both with their one electron here, they can share. So now we have two nuclei that are positively charged due to the protons are both able to see two electrons. So that makes them more electrostatically satisfied than if they had just been on their own seeing one electron. Because seeing two is a lot better in their opinion than seeing one. So this is kind of a picture of what it means to bond. And we'll get to antibonding here in a minute. But, so we know that atoms will bond in order to make their electrostatic requirements more satisfied. And one thing that is interesting in research is that the normal, kind of standard length for one bond is 1 ampere. You may sometimes see that written as 1A with a little circle on top, 1 ampere. And that's the length of one wave of an electron. So it works out really well in that matter. And speaking of waves, since we know that this electron cloud is like a wave, we can describe it mathematically as a wave. When we add together waves, we know that there's only two ways they can add, either completely constructively or completely destructively. When they add constructively, the waves will combine and they'll both be of the same amplitude. So the end result, you'll get a wave with even a greater amplitude. However, when the waves combine destructively, you'll have one wave of a positive amplitude that will cancel out with one wave of a negative amplitude. So those will end up canceling out and adding destructively. So now we're going to transfer this idea of adding waves over to making bonds. Let me erase this, give us a little more room. Okay, so we know that atoms bond together to make molecules. So when we're talking about this in terms of atoms, we're going to have atoms combining their orbitals, their waves, in order to make molecules. And you'll sometimes see this written as LCAO. And that stands for the linear combination of atomic orbitals. So the idea behind that is you combine atomic orbitals to make molecular orbitals. So this is how we get molecules. Okay, so let's just start with a simple situation that we can kind of compare to our kids with the candy. So hydrogen. We know that hydrogen has one electron. Okay, and so we're going to call that the 1s. Okay, so let's say it's going to combine or going to bond with another hydrogen atom, which also has a 1s electron. Okay, and we know that the shape of the 1s orbital is spherical. We can kind of compare it to a cotton ball. I have one here. It's kind of like a cotton ball is more dense on the inside and kind of gets a little fluffier as you go out, not quite as dense. You can kind of think of a 1s orbital that way. In a 1s orbital, the electron density, like where the electron mostly is really close to the nucleus, and it kind of fades as you go out. So, we're going to combine these two 1s orbitals. And we know, like when we add waves, they can either combine completely constructively or completely destructively. So let's draw out our two options. So for constructive, that's going to be bonding, where both nuclei can see both electrons. So here's how we'll represent that. There we go. So we have two nuclei can see both electrons. Okay, so this is like our waves adding constructively. But on the other hand, they can also add destructively, meaning one will have an opposite sign of the amplitude. And when that happens, that only allows one nuclei to see its one electron. So instead of placing the electron density between the two nuclei, each nuclei can only see its electron. And this is what we call the antibonding state. So you can see here, they're not as happy as in the bonding, because each nuclei, here each kid, only gets to see one piece of candy, because there's what's called a node between them. And a node is just an area where you don't have any electron density. It's an area of zero density right there that separates them. Okay, so we have bonding and antibonding. And if we look at this in terms of energy, from your previous freshman chemistry class, you're probably familiar with energy diagrams when building orbitals. So we can label this as your energy. It goes up, and then you'll have, we'll draw this as our 1s orbital, each with one electron. Okay, and they can either combine in a bonding fashion, which is like the waves adding constructively, and that lowers the energy, or they can combine in an anti-bonding fashion, a destructive manner, which will raise the energy. And just for note, if you ever see the little stripes on the orbital, that's just indicating that the amplitude is of an opposite sign. Alright, and what we'll come to find out, kind of connecting this to what you're going to learn on down the road, is that it matters where the electron density is. If it's between the nuclei, it's going to be involved in a bond. But if it's not between the nuclei, that creates an antibonding orbital where it has a spot for electrons, but it's in a different place. And we'll see that in reactions. A lot of times we'll put electrons into these empty anti-bonding orbitals. And that'll affect, where different molecules attack. But we'll get to that later, so just something to think about. Alright, well, keep enjoying the class.